We have a formula for the derivative of the inverse hyperbolic secant, so we want to use that to motivate a new integral formula like we've done for the inverse hyperbolic sine and the inverse hyperbolic tangent. So what we want to do is start with our derivative formula, that is for a differentiable function u living between 0 and 1, we have the derivative of the inverse hyperbolic secant of u is the additive inverse of u prime divided by u times the square root of 1 minus u squared. So of course, if we just work this backwards, this will give us a basic integral formula of the integral of du over u times the square root of 1 minus u squared will actually now be the negative of the inverse hyperbolic secant of u plus c, or using our formula for the inverse hyperbolic secant, the negative of the natural log of 1 plus the square root of 1 minus u squared divided by u plus a constant c. So we got to know this formula pretty well when we were deriving this. So again, like I said before, when we did the integral problem with the differential equation with the inverse hyperbolic tangent, we found it was useful to use this type of form instead of the more elaborate form, basically because it made the problem work forward much more quickly and much more efficiently. So oftentimes you don't want to say that one integral form is better than another. It just really depends on what type of problem you're trying to do. So now what we want to do is say, okay, let's make this integral more user-friendly. So we're going to fix an a positive, and then we'll just let u, the absolute value of u divided by a, live between 0 and 1. So we want to extend the formula to the absolute value to make it even more user-friendly. So now what we have, our du will be, of course, replaced by 1 over a du, and we replace all the u's with u over a to get this. Now, of course, these a's here absorb, but now notice when we get a common denominator here and extract the 1 over a, we have 1 over a, which now runs into the numerator. And so we get the integral of a du over u times the square root of a squared plus u squared. So the same algebra we've been doing many times before. And so, of course, we can factor the a. But now this will be equal to the negative of the inverse hyperbolic secant of u over a plus some constant c1, which is also equal to this, where we replace u with u over a. And again, the same thing ensues. The u over a here, we get a 1 over a, and we're going to have the same thing here. We're going to have a 1 over a when we get a common denominator, and those a's will absorb, but that will leave behind the negative of the natural log of a plus the square root of a squared minus u squared divided by u, then plus some arbitrary constant c1. But now we know that these are all equal to this integral, and so we just want to isolate this particular object. So we have the integral of du over u times the square root of a squared minus u squared will now be the negative 1 over a of the inverse hyperbolic secant of the absolute value of u over a plus c, or using the log form, the negative 1 over a natural log a plus the square root of a squared minus u squared divided by the absolute value of u plus a constant. So again, when we look back at this particular example, we've seen this many times. The a's or the common denominators absorb in the fraction, just like when we were deriving the formula for the derivative here. So again, we're seeing the same type of algebra and the same type of computation recur over and over. But it's really important also to know that when you produce these Pythagorean style integrands, there are many ways to actually compute integrals like this. You will find other techniques, but sometimes it's convenient to have a form that you remember, that you use often enough, that you keep in your brain. So again, add this to the list that we already have for the inverse hyperbolic sine form, the inverse hyperbolic tangent form, and the inverse hyperbolic secant form. And we are done.